then the Lagrangian, the definition for the Lagrangian is t minus u. So the Lagrangian is defined as t minus u, like that. And the first question I had, I guess most people have, is why t minus u? Why not t plus 2u, 2t minus 5u? Why just t minus u? So here's my idea. This is not a perfect, what you say, definition. It's not a definition, it's just my intuition behind this. So this is how I think about it. Let's say I push on a rock. This is a stupid rock, and I push on it. Now, let's say that we're looking at the rock as the system. Now, for the system to change its state, I think an acceleration, like changing its state, for the system to change its state, I have to apply some force on it. Its resistance to change is its inertia. So I have some force I apply on it. Then I have M and then A, of course. And its ability to resist the force I apply on it is, of course, its inertia. So you could say the internal that's resist me trying to change the state is its inertia, and the environments, you could say what is from the outside is the force I apply on it. It's an external force on the object, and the internal way of resisting it is the inertia itself. Now we can apply this same idea to kinetic and potential energy. If you studied something like orbital mechanics, let's say you had a blazingly hot sun here, and you had an asteroid approaching the sun. It doesn't need to be the sun, it can be any massive object. So the path, that's because of the mass of the sun or whatever huge mass it is a planet or something, it will cause the asteroid to change its trajectory as a parabola or hyperbola, or if the energy of the asteroid isn't big enough, it will get trapped. And this, for me, the same idea. The internal, you could say, resistance towards the environment is its kinetic energy. If its kinetic energy is high enough, it won't get trapped in the gravitational pull of, in this example, the sun, right? If the gravitational pull is too big compared to the kinetic energy, it will get trapped and go around the sun or just spiral in. It actually depends. I think it would just go around the sun. Yeah, I think the kinetic energy has to be very low. I'm not quite sure, but at least I know that it won't continue its trajectory if its kinetic energy isn't big enough compared to the potential energy, and will get trapped in the gravitational pull of the sun. We usually model this if I have energy here, and I have a graph, and I model its potential energy like this, and we have this energy well here. You will have some point where it will have negative energy and get trapped. That's the idea. So if it gets inside of here, it will get trapped in the gravitational pull of the sun. Otherwise, it will continue its trajectory, change its shape, hyperbola, parabola, doesn't matter. In this case, just a demonstration. But what I'm trying to, I don't remember the details, but what I'm trying to say is just conveying the idea. So what I'm trying to say is that if I threw, for example, this pen, the trajectory of the pen is its internal resistance to the environments, the kinetic energy, and the environment itself, right? So how far it will go is how much it will resist, which is kinetic energy, and how strong the environment is. So the environment will have a negative impact on the trajectory of the pen itself, similar to the asteroid here, right? That's why I think it's T minus U works, because T is how far it will go, but U is like, no, you can't go further, right? And the same here with the asteroid. The asteroid will continue its trajectory. It resists the gravitational pull outside as much as it can, right? But its path is determined by how much it resists and how strong, you could say, the pull of the environment is, right? So that's just my idea of it. It's not a definition. So yeah, I just keep it simple like that. Okay, that's the way I think about it. Okay.